Hey, everybody. You see the problem on the screen right now? Find it all is what I put up on top. There we have a bit of a quadratic application. A baseball being hit. Find some key values, and in the end, we're going to go and put everything together. Okay, here we go. I'm going to shrink that down a little bit just to give us some room to work underneath. The problem asks us in A, what is the maximum height of the ball? So if I was to work my way through on A, I know that maximums and minimums happen at the vertex. And so I can read the vertex from the equation of that parabola. I can see that my vertex is at 2.5, 38.5. That is the location of the vertex. So when the question asks me what is the maximum height of the ball, I am looking for the maximum value of that function, and that maximum value is always the y-coordinate, or in this case, the h-coordinate. And so if I was looking to answer the question for A, I can just read it straight from the equation. I could say then 38.5 meters. There we go. Hopefully not too bad. Second question asks us, what is the height of the ball when it was hit? So if I was to work my way through that one, the height of the ball when it was hit. Well, the function represents height over time, and specifically my time was since the ball was hit. So if I'm looking for when the ball was hit, I'm actually looking for when no time has passed. That is when t equals 0. So what I can do is I can sub in that t equals 0 value, and I can now solve, or I should say simplify. You'll notice I do not have an equation to solve. I simply have something to calculate. So let's just work our way through BEDMAS. I have to make sure that I deal with the exponent first, or the operation inside. So I'm going to have 0 minus 2.5. That is negative 2.5. Square that is going to give me 6.25. And I can slowly work my way through order of operations. Now I can deal with my multiply, my negative 6 times my 6.25. That's a negative 37.5. And when I then add that to 38.5, I get down to 1. What am I measuring in this case? Height, and height is in meters. There we go. So hopefully A and B make sense. I'm hoping that that's pretty straightforward in terms of application. Okay, let's work our way through maybe a little bit of an uglier one. Let's take a look at that question C now. How many seconds after it was hit did the ball hit the ground? And we need to find that to the nearest second. So I'm going to just shrink that down again to give us a little bit of room to work. How many seconds after it was hit did the ball hit the ground? So I start to think about, well, what's happening at the ground? And if I look at the function is the height, h in meters. So if I'm thinking about on the ground, that means I am no meters above the ground. I'm looking for when is the height equal to 0. There's my key on question C. So I can go through and I can replace my height in my function with 0. Now this is going to give me an equation to solve. You can notice you have your variable in one spot. There's your t. We're going to solve this equation. Now, depending on the course you're taking this problem in, you may have different expectations as to how to solve this. What I'm going to do is I'm going to solve this for what I would argue would be your most advanced level, and then I'll show you where you can kind of take different routes through depending on the course you're taking. So for us to work our way through that equation, we could take that red equation as it's written and go ahead and expand our brackets and collect like terms. I'm hoping, though, we can notice we're going to create an equation that has a t squared in it, and we'll create an equation with a single t term in it. We won't be able to collect those, so we're going to have to go through and look to factor or use quadratic formula. I don't want to do that if I can avoid it. Look at your red equation right now and notice your t is in one spot. And if my t is in one term, then what I want to do is I want to isolate it. So I'm going to fight the urge to go through and expand brackets and collect like terms, and instead I'm going to isolate for t. Okay, we'll take this nice and slow. I have two terms on the right side of my equal sign. I have my first big ugly term, and then I got my nice neat term on the end. I'm going to get rid of that second term. So for me to get rid of my plus 38.5, then I'm going to minus 38.5. And I can slowly and methodically work my way through to isolate for t. Now I've got my t term all by itself. Now I want to go through and isolate for t. So now what I'm going to do is I'm going to divide out that coefficient of -6. So to get rid of a times by -6, I'm going to divide by -6. Well, pretty quickly I'm hoping we can see a negative divided by a negative is a positive. And so we're going to get 38.5 divided by 6 is going to equal t minus 2.5 all squared. Now, here's one of those roads that we talked about where you may be hopping off and taking a certain route. Depending on the level you're working at, you may be okay to keep that left side simply as a fraction, even with that fraction unsimplified. If you are, then the next step would be to focus in on the squared and isolate by getting rid of the squared, which means taking a square root and so on. Now you're working with approximates probably as you work your way through. I'm going to take a different approach. So I'm not going to focus in on that squared yet. What I'm going to do is I'm going to look at that fraction on the left side. Now, there's a certain number of things you should try. First off, we should be trying to see, does 38.5 divided by 6 give us a terminating decimal? Now, you go through and you calculate 38 divided by 6, and you're going to notice that you're going to get something ugly like 6.416 repeated. Ugh, big ugly decimal. I do not want to work with big ugly decimals like that, and we're probably going to end up rounding them. And as soon as we round them, we're wrong. We're a little bit off. So I want to fight the urge to round. So I'm going to leave that as a fraction. My only problem is I have a decimal in a fraction, and that's unsimplified. So what I can do is I can multiply the top of that fraction by 10 and multiply the bottom of the fraction by 10. You'll notice that that green fraction I just wrote down was 10 divided by 10. That is a value of 1. And if I multiply something by 1, I don't change its value. So I could change my fraction to that, which gives me at least a better simplified fraction. I don't have a decimal inside my fraction. However, we'll notice that that fraction on the left side is unsimplified. So what I can do is I can see that if I divide the top and bottom both by 5, my top is going to work down to 77 and my bottom 12. And now I know that that fraction is fully simplified. Now, I can see that it's fully simplified because 77 is just a 7 times 11, and 12 would be a 4 times 3, and I can see that there are no common factors in the top or the bottom. I'm going to leave those blue factor trees there just for a little bit longer because they can help us with where we're about to go. Okay, now that left side is a fully simplified fraction, I'm going to keep going. So now my focus becomes eliminating the squared. Well, I can eliminate my squared by taking a square root. So I'm going to take the square root of 77/12. Just don't forget that every time you take the square root, you could have a positive or a negative value. Okay, I'm getting there. Now I'm going to take the square root of both parts of that fraction. which means to take the square root of the top and the bottom. Okay, so now I have the plus or minus root 77 over root 12 is equal to t minus 2.5. Okay, I've got so many ways to go on this. My problem is that fraction on the left side, if we zero in on that a little bit, it has a radical on the denominator. And trying to take something and divide it by an irrational number of times, trying to break it up into an irrational number of groups, just doesn't make sense. And so our focus on that root 12 becomes, let's rationalize the denominator. Now, there's a couple things you could do. We could simplify that radical first, but I'm just going to deal with it exactly as written. I'm going to rationalize that fraction. So I'm going to multiply by a form of 1 again. And I'm going to multiply by root 12 over root 12. You'll notice my purple fraction is still a value of 1, so I did not change the value. What's that going to give me? Well, it's going to give me something really ugly on the top. But don't freak out over how big this number becomes. Yes, 77 times 12 is going to give me 924, but it's actually going to be pretty easy to work with. On the bottom, I'm going to have 12. And that is still equal to t minus 2.5. Okay, let's keep it going. Well, my problem is I need to reduce root 924 if it does. So now I would be doing a factor tree, and I'd be going through and trying to break up 924 and going, oh my goodness, that's such a big... Stop for a second and take a look back at the factor trees I have on the left side. I already know what makes up 924. It was 77 times 12. And my 77 was a 7 times 11, and my 12 was a 4 times a 3. So I can actually see how to reduce that radical right now. I'm able to take the square root of the 4, which is the 2, but I'm not able to take the square root of the rest. So if I calculate, maybe my 3 times my 7, there's 21, and then 21 times 11, there is my 231. That is all over 12. Yikes, this has turned into an ugly expression. Okay, let's keep it going. So I'm going to wrap back around here. Now, maybe you take a look at the fraction on the left side and you notice, hey, I can reduce that. A 2 divides into itself once and then into 12 6 times. And so if I isolate for t, that means I'm going to get rid of the minus 2.5. Okay, I'm just going to write everything left to right because that's the way I read. So I know my t will be all by itself. To get rid of a minus 2.5, I'm going to add 2.5. Then I have plus or minus the root of, I'm not going to write the 1 because that's bad form, all over 6. Okay, I am almost there. Now I just want to simplify that into one term. So I'm going to take that 6 in that denominator and I'm going to get a common denominator with the 2.5. So I'm going to have to multiply that 2.5 by 6, and that is going to give me 15. And there are the perfect answers for that problem. Perfect. You'll notice there is no rounding anywhere in that solution. Okay, the question asked us, how many seconds after it was hit did the ball hit the ground to the nearest second? So we're not going to answer that way, although those solutions are perfect. What we're going to do is we're going to change them into decimals. You will notice that that line that I just put the blue star beside is going to look an awful lot like the solutions you would get had you expanded, collected like terms, and then used quadratic formula. Okay, here we go. Let's calculate the positive case. So if I calculate 15 plus root 231 divided by 6, that's going to give me an approximate, and you'll notice I put a dot above my equal sign to show my rounded value, I'm going to round that, and I get 5.03 seconds. Now, the question asked me to round to the nearest second. I'll do that in a moment, but that's my approximate. So you make sure that your keying sequence can get you to that. Now, what I'm going to do is I'll follow the rounding rules in the problem, 5 seconds. But I also get another case. If I calculated my 15 minus root 231 all over 6, I'm going to get a negative 0.03 seconds. Now, there's a couple things to consider in this problem. First off, you just solved for t and you found a negative value. That is a negative time. Well, we can't have negative times, and so I would rule that out. Secondly, though, this function represents the height of the ball after it was hit. So our function doesn't really represent the height of the ball before it was hit, which means that negative time I would have to rule out as inadmissible. It is a value that is a solution to the equation, but not one that I could accept because of the application. There we go. We got our solution. 5 seconds. Wow, look at all that red. Okay, I think that that's your doozy algebraically. You will notice if I shrink everything down and go back, and you'll see me put a big gold star beside that 38.5 divided by 6 line, you may have been able to go through and work from approximates at that point. Okay, you make sure you're good on what the expectation is. Okay, let's jump into that last problem. Okay, now we're going to work our way through and we're going to solve for D. D says find the height of the ball 1 second after it's hit. Okay, this seems a lot more straightforward. That means I need to sub in a t value of 1. Okay, that means that I'm going to have my height, and it's negative 6 times 1 minus 2.5 squared plus 38.5. Okay, now my expression on the right side simply needs to be followed all I need to do is follow bedmass. So I'm going to get my negative 1.5, and I'm going to have to square that first. So I'm not going to touch the negative 0.6. I take 1.5, square it, and that is going to give me a 2.25. Now when I multiply that by negative 6, that's going to give me a negative 13.5. And now when I collect that whole thing together, that is going to get me to 25, and I'm talking about meters for units. Okay, there we go. Hopefully not too bad. Okay, what I want to do is I want to put a bunch of stuff together just so we can see how this function represents this application. Okay, we're going to sum it all up in a moment. Okay, so I just put all of our problems up on the top again, and now what I'm going to do is I'm going to build the function. So I have a vertical axis that represents height, and I have a horizontal axis that represents time. And if I just used what I found, look at question B first. What was the height of the ball when it was hit? Well, we found out that that was at 1 meter. So my function is going to start at 1 meter. Then the baseball goes up into the air, comes down, and hits the ground. Well, question A asked, what was the height or the maximum height of the ball? That would be us finding our vertex. And you'll notice back in question A, the maximum height of the ball was 38.5. Well, we can actually go a little further. We know when it happens as well. We know that it happens 2.5 seconds into its flight. So I could label the coordinates of my vertex. Okay, let's take a look at C, the big ugly problem. We worked our way through, and we came up with, when does that ball hit the ground? So on question C, we found out over here That was at 5 seconds. Now, I want to put a couple things together for us as we go. First off, remember that inadmissible solution? Well, I'm going to backtrack a little bit. My parabola for the function given actually does this and does this. All of that extra pink stuff. It's just that for the application, that pink part doesn't apply. So you may be able to see where that negative 0.03 second solution would be an intercept on our function, but it wouldn't apply when the function represents a baseball's flight. Okay, part D. Part D, we went through and we said, hey, find the height of the ball 1 second after it was hit. And so what we noticed is if we go 1 second in and we go all the way up, we found the answer in part D. We found that that was at 25 meters. So if I take off all of that blue stuff now, and I actually just label it, and I say that that point would now exist at 125. Okay, nice. Now, there's a couple of, or maybe one other big thing that I want to make sure we're good with. When we actually found the answer to D, we also found another point. I'm hoping we're good that we recognize that that parabola has an axis of symmetry, a line that runs straight down the middle that makes one half of the parabola a mirror image of the other. So I can tell that 1.5 seconds to the left of the vertex, we were at a height of 25. So I know then that 1.5 seconds to the right, we would also be at a height of 25. And so what I find then is at 4 seconds, we're also at a height of 25. So I'm hoping that that gives you some extra information. Little side note, just in case anybody's getting distracted at the bottom of that graph, or I shouldn't even say the bottom, on our t-intercepts, remember that we did a little bit of rounding on that orange solution of 5 seconds. It was actually 5.03. If that helps out, just to make sure you can see the parabola is symmetrical. Okay, there was a bunch of stuff in that problem. But I'm hoping if you were looking for a little bit of help walking through a quadratic application, a pretty traditional one, a ball's flight through the air, that these solutions can help you out. Okay, best of luck with your problem solving.